And I want to talk about a really specific one. The molecule I want to work with all of you this semester with is this particular cycloalkane. I'm just going to move this down just a little bit. This is a trans 1,2 disubstituted compound where we have bromine and a methyl group. Bromine and a methyl group. We're going to use this exercise today in our remaining 15 minutes together to revisit chair conformations. And this is also going to reinforce what we were just doing with Newman projections, and the question that both the two students just asked is going to reinforce. Both of those two questions actually are programmed into this example. So we're going to take this particular compound and we're going to react it with sodium ethoxide. Let's just use that one. And I want you, just for fun, draw on what product or products you might think we would get here. Maybe not doing a mechanism fully, but maybe like looking at this very briefly and identifying maybe alpha, beta. Oh, I guess there's two different beta positions. Could you sketch out what you think some products might be from this reaction? Just from this little setup, and that means not the mechanism per se, but we're going to lose a hydrogen, we're going to lose the bromine, and we're going to have double bonds in some places. What would some of those products look like? Maybe there's 1, 2, 3, 4. I don't know what you would come up with, but just sketch something right away. Like, let's just anticipate or think or make a quick prediction based on what knowledge you have now. And what knowledge you have now might not be enough to solve this perfectly, but what are some answers you think we might have here? And then, now we're going to practice this problem. Chairs present a unique conundrum for us when we have cyclohexane rings. When we have a cyclohexane ring, our expansion, right, when we're expanding at the beta positions, when we use a cyclohexane molecule, our expansion must use a chair conformation to do this, okay? So when we have a cyclohexane ring, when we do our expansion, right, we draw the hydrogens at beta positions, we're going to have to do it in a chair, unfortunately. So some of you, I hope you got 2 answers here, or maybe 3, but really only 1 forms from this reaction, and we're going to use a chair to figure this out right now. Let's, I'm going to make sure this camera is right, a little bit better than I usually do. I'm going to draw a chair. My chairs aren't the best. I haven't practiced them as much as you have this semester. That's good enough. We draw a chair, we draw all our axial positions in and equatorial. And we're going to have to draw on some atoms on this thing. And I'm going to put my methyl group here, hydrogen here, bromine here, hydrogen here. I'm going to fill in 2 hydrogens here. So I want you to fill in this much of our chair. This is our alpha position. This is our beta 2 position. This is our beta 1 position. That follows from what I had labeled right up here. So I know this takes time. I'm going to pause here and make sure you have enough time. But I've decided to draw this in the equatorial conformation, the most stable conformation. And I've only expanded the alpha, the beta 2, the beta 1 position. These 2 things are both trans to one another still. This is up and this is down. And they're both equatorial or di-equatorial. So you guys would predict that this would be the more stable product. The other one will have these groups axial, and we know equatorial is more stable than axial. Beta 2. At beta 1, we have 2 hydrogens. I'm going to write this analysis over here. At beta 1, we have an axial hydrogen and we have an equatorial hydrogen. Make sure you can identify them. So at this beta 1 position, we have axial and equatorial. And at the beta 2 position, You have an axial hydrogen. So these are only the 3 hydrogens we have that are actually a beta to this alpha position. We have 1, 2, 3. I've labeled them beta 1, axial, beta 1, equatorial, beta 2, axial. We're going to do a thought exercise now and figure out if any of these are reactive. To be reactive, they have to be either 180 degrees or 0 degrees to our leaving group. This is why I don't draw tables very often. It's off to a bad start, but maybe it's a mundane. Let's look at the beta 1 position. Let's look at its axial hydrogen. What's the relationship between this hydrogen and this bromine in bond angles? Think about chairs for a minute. If we were looking down this bond, this is axial and up. This is equatorial and kind of up into the sideways. If I was looking down this beta 1 alpha bond, this hydrogen would be up here, and bromine is actually going to be here. And they'll be 60 degrees apart from one another. It's okay. Thanks, Drake. I really appreciate it. But think about this for a minute. If you don't see this, then you need to build these models again. But this is up and axial. And then bromine, if we're looking at it in the back, is equatorial. It goes about like that. The bond angle relationship for here to here is actually 60 degrees. So it doesn't work at 80, it doesn't work at 0 degrees. Maybe we should write the 60 in the middle. What about this equatorial one? So I gave you the answer, and I do appreciate that someone chimed in what they thought it would be. I really appreciate that. Okay, here we have the beta 1 equatorial, and this is an equatorial position. Imagine looking down this bond again. Are these staggered? Are they eclipsed? Are they anti? Are they syn? Or what is the bond angle relationship between this hydrogen and this bromine? Right? Anti is 180 degrees apart. That's what anti means. So these two are 180 apart. It's one possible answer. I think you could follow Drake's lead and write JK after it. This is equatorial, goes down a little bit. This is equatorial, it goes up a little bit. I don't have my model kit built with me today. This one is, right, if we're looking at this carbon from the back, hydrogen, this is the axial one. This is the equatorial one. Not working. So this one's about pointed some way that direction down, this hydrogen. If we're looking at it down here. It's equatorial and going down. It has an axial position, but this one's equatorial and going down. This bromine here is equatorial and going up. It would look something like this in the back. Like that. It would also be 60 degrees. Not 0, not 180. You'll have to build this for yourself if you're having trouble with it. And it's okay, you guys are guessing, you guys are thinking. I know you're not just guessing. I know in your minds you think these are 180 degrees apart. They're not. If this is in an equatorial position, axial adjacent to it will always be 60 degrees, and equatorial adjacent to it will always be 60 degrees. Maybe it's easier to see looking up this one. Let's do it up this particular bond. Let's look at the beta 2 position. We have a hydrogen that's axial, and this is equatorial. This is almost like a sawhorse projection here. This is almost like a sawhorse projection we were drawing earlier. We're looking down this particular bond here. This is alpha, where we have a leaving group, and in the back we have beta 2. This hydrogen's axial and up, and this bromine in the front. So this is axial and up in the back. This is my hydrogen in the back. And this bromine in the front is like this to them. What's the relationship between these two things? Or if we're looking down this bond, bromine's up, hydrogen's vertical. This will be 60 degrees. The relationship between an equatorial substituent and an axial one beta to it will be 60 degrees. Okay, what about this bromine in this methyl group? The methyl group is not reactive. All right, that's not the point. This definitely will not react under any circumstances. There's no hydrogen here. But what's the relationship between these two groups looking down this bond? The relationship, what I mean is it 0 degrees? Are they eclipsed? Is it 180 degrees? Are they anti? Is it 90 degrees, 60 degrees, 120? These are 60 degrees. Thanks so much, Christina. Appreciate it. These are definitely gouged to one another. If we're actually looking down here, this is also gouged to it. If you build a chair, the reason why a chair is so stable, because every bond is staggered. If you look down this bond, staggered, 60 degrees, 60 degrees. If you look down this bond, all the groups will be staggered to one another. That's why a chair is so stable. So when this bromine atom is in an equatorial position, everything beta to it is 60 degrees apart from it. Please build this if what I've just said is completely fiction or fanciful for you. If you don't have the model kit, shame on you. You should have got it or should have talked to us sooner. We could have done something about it. Go into the textbook and look at chairs and just look down these bonds. So nothing lines up 180 or 60. You should build or look in the textbook if you really struggle with this, or when I gave an explanation and you still didn't understand what I'm saying, look it up, please, or we can talk about it in office hours later, but I'm not going to talk about it more. So this conformation, at the end of all this work, is unreactive. This conformation just doesn't react. I left a little bit of space here. I'm going to use this, but if you're going downward in your notes, that's absolutely fine. But what I want to do here is I want to do a ring flip for this. I'm going to do a ring flip or chair conformation flip, putting all groups that were equatorial, axial, and vice versa. Well, this chair is already off to a bad start, but I have confidence that I'll be able to pull it off in the end. So this is the chair that I'm drawing here. Alpha, beta 2, beta 1. It's not my best chair, but do your best to draw a chair. It'll be right if these two groups are trans, if bromine is up in axial, methyl group is down in axial. I'm trying to draw the alpha carbon here. Beta 2, beta 1. Let's look at these positions again. At beta 1, we have a hydrogen that's equatorial. We have a hydrogen that's axial. At beta 2, we have a hydrogen that's equatorial. Let's go down the list here and try and fill in what these bond angles are to bromine. Beta 1, equatorial. This is equatorial. This is axial. Very hard to see from my diagram. Maybe from your chair you can see it better, or from our discussion we just had, when one group is equatorial, the other one is axial, the relationship between these two things is 60 degrees. Build it, see for yourself, but this is equatorial, that's axial, this is up and in the back, and our hydrogen being in the front. If we're looking down it, we have 60 degrees here. What about this axial hydrogen and this bromine atom? This is axial down, this is axial up now. If we were looking down this bond, the group in the front is axial and down, means vertical down. The group in the back is vertical up. What's that bond angle relationship? Down, up, vertical. Front hydrogen is down, back group is up. Bromine's at the top, hydrogen's at the bottom. This is anti. This is 180 degrees. This is reactive. This hydrogen here, I'm going to circle it. In this conformation only is definitely reactive. It will lead to products. 180 degrees, perfect. Don't give up. We didn't finish. We left one box here. Beta 2 position has a methyl group, unreactive. Has a hydrogen atom here. It's equatorial. This is axial. Axial is up. Equatorial is 60 degrees. So this is perfectly straight up. You could call it 180 or you could call it 0. And this is 60 degrees up. Either way, these things don't line up. These will have a 60 degrees disposition to one another. So please practice this particular chair example. I'll give you a blank one in a minute to practice. I'm working on. But this one reacts. This bromine leaves. So if we're doing a mechanism here, base can come in. It can only react with this hydrogen. Double bond will form here. Bromine will leave. And I'm hopeful that one of the products you drew from the beginning might have been this one, right? That some of you drew at least a product here from the beginning with a double bond here. And I suspect some of you might have drawn double bond here as well. And that's okay for the beginning, but this is the only product we make from this particular reaction. We went through a lot of trouble here to do this. Here's the tip. When you take this particular molecule and you do your expansion in a chair, directly put the leaving group in an axial position. When the leaving group was in an equatorial position, no matter how many hydrogens we had surrounding it, none of them could react. They all had 60-degree angles. So when bromine is equatorial, these hydrogens are all 60 degrees apart from it. They can't react. But when bromine is axial, then if we can find adjacent axial hydrogens, just one, then it can react there. So the trick for our expansion using chairs, put the leaving group in an axial position, then explore all beta positions for axial hydrogens. I'm not going to write that out, it's a mouthful, but the moral of the story, if we look at this very carefully, in the equatorial or more stable conformation for this molecule, none of the beta hydrogens can line up properly. If we put it in a less stable conformation, but put bromine axial, we now have a chance to find reactive hydrogen atoms. Let's do one more example in our notes for you to work on your own, and then we'll do